This is Lab 3, Analyzing a Star Orbiting a Black Hole. In this introduction, we can see that we are given a file of comma-separated values containing x and y coordinates of a star in orbit. The software of VPython as well as given constants were used to determine the black hole's mass. We are assuming that there is no change in the mass of the star or the black hole, and the only force acting on the star is the gravitational force due to the black hole. With the black hole located at negative 1 e to the 10, 3 e to the 10, 0 meters, which is used as the origin, and the star's mass being 1.989 e to the 30 kilograms, we were able to find a result mass of the black hole being 3.835 e to the 31 kilograms. This calculation was made through the use of data, the information given, Newton's second law, and Newton's gravitational principle. We were able to manipulate and find the needed values by changing the parameters in VPython. Here we can see that the origin was the position vector of the black hole with radius of 7 e to the 10. The star was given a radius of 3 e to the 10. And the star's mass was given as about 1.9 e to the 30. Delta T was 86,400 seconds, which is the number of seconds in a day. We called on the x and y values from the CSV files, and we're able to get a change in x position and y position, which was used to find V initial and V final. We were also able to input that to find the momentum using the star's mass and delta V and delta P as well. Using the values given above, we were able to find dp dt and apply that to equal Fnet. But as we can see, as stated before, that Fnet is solely relied on Newton's gravitational force, which was then used to find the mass of the black hole. We manipulated the Fnet equal to the gravitational constant times the mass of the star times the mass of the black hole over the radius squared right here, and isolated the mass of the black hole and made that an output in our Python simulation. The arrow scale was closest and best visualized at 1.5 e to the negative 19. We were able to see that, for the most part, the gravitational force was pointing towards the black hole for all of the orbit. So, as a concept question, we were to discuss how Fnet, perpendicular, parallel, and Fnet are different from dp/dt, perpendicular, dp/dt, parallel, and dp/dt. We can tell that Fnet components incorporate only the gravitational force, while dp/dt components are instantaneous and relative to motion, while Fnet components are dependent only on the constant gravitational force. We must also remember that momentum is caused by the net force acting upon the system, which means that net force is the force acting on the system of the star, while momentum is an effect of that force. So, as a what if, we were to imagine that the black hole whose mass you found was removed and a different black hole was placed in the same location. We are to assume that the motion of the observed star remains unchanged, but is still assumed to be affected only by the gravitational force. Well, we wouldn't be able to tell much of a difference from the motion of the star because, as said before, if F net is only the gravitational force made by the black hole, and this does not change, then we are to assume that the new star must have the same mass of the original. Because if the motion of the star goes unchanged, then the gravitational force acting on the star must have remained the same. In conclusion, we can tell that the simulation of the star's orbit around the black hole was well fitted using the Python simulation software. The Newton's gravitational principle and Newton's second law were applied and manipulated to resemble and model these stellar objects and to calculate the mass of the black hole.